So this is problem number 2 from the 2011 AP Calc AB exam. This is Form B, so it's the second form of the exam, and this is a calculator problem. And basically the setup is there's a tank that's holding water and it's filled to capacity 12,000 liters. At time t equals 0, water is drained out of the tank, modeled by R of t, measured in liters per hour. So this is the rate of change of the amount of water in the tank, where R is defined to be here. In part A, we want to determine whether or not R is continuous at t equals 5. So three things have to happen in order for us to be continuous at a given, in this case, t value. We have to make sure R of 5 exists, and if you put 5 here and 5 here, since this is the inequality we'd be sitting on if we're equal to 5, you definitely get something that's defined, so R of 5 will exist. The second thing, and this is the thing that usually happens, especially on a piecewise graph, whenever you're not continuous, your limit has to be existing. So your one-sided limits have to be equal to each other. So I check the limit as we approach 5 from the smaller side. And on the smaller side of 5, we'd be dealing with this rule for the function. And so if I take that rule for the function, toss it into the limit, and then put 5 in place of the t's, I end up with a value of 375 for the limit as we approach 5 from the smaller side. Now as you approach 5 from the bigger side, the values of t bigger than 5 will be in this inequality, so we'll be dealing with this rule for the function. And so I toss that into the limit, and just like we did in the first part, put 5 in place of the t. And if you evaluate this on the calculator, you get about 367. Since these two one-sided limits are not equal to each other, the limit as we approach 5 does not exist. So since the limit doesn't exist, our function is discontinuous at 5. In part B, we want to find the average rate at which the water is draining between t equals 0 and t equals 8. So here's our formula for the average value of a function that we've used a bunch of times over the course of the year. And then if we want the average value of r from 0 to 8, we're just going to have 8 there, 0 there, 8 here, 0 there, and then the function r of t here. Now the one tricky thing is that when you go from 0 to 8 on r of t, you cross the t value where the definition of the function changes from this rational function to this exponential function. So I had to split this integral up into two separate halves, or not, I should call them halves because they're not equal to each other, but two separate pieces. From 0 to 5, the function would be defined to be this, and then from 5 to 8, the function would be defined to be this. So if you evaluated this on the calculator, evaluated this on the calculator, since it's a calculator problem, added the results together, and then multiplied by 1/8, you end up with about 258 liters per hour as the average rate of change. Part C asks us to find r prime of 3 and then try to explain what the meaning of this is within the context of the problem. So the way that I personally did this was on the calculator, and I started with a graph of not all of r of t. I want to know what r prime of 3 is, so I'm going to graph the first part of the function here. So I'm going to have 600 x over x plus 3. And if I graph this, I don't see very much on the standard viewing window. I can definitely, go into my table and try to figure out a more appropriate viewing window by seeing that, well, I'm going to have to see up to numbers in the 300s, 400s, and if I go down in the table, probably well above that even. So yeah, up into the 500s. So if you want to see a little bit more of the graph, you can definitely change that to 0, change this to something like 500. You can change your scaling as well if you wanted to, but there's your graph. And what we want to do is we want to know r prime of 3. Now, if we wanted r prime of t, we wouldn't be able to use the calculator to do this. But if we just want to know the derivative of something evaluated at a single point, all we have to do is have the graph on the screen, go into the calculate menu, dy dx will give us the derivative at whatever value we type in. We want the derivative evaluated at 3. There's your derivative evaluated at 3. So the one downside to this is supposed to be exactly 50. Like if you took the derivative of this using the quotient rule and then put 3 in place of the t's, you would get exactly 50. So the calculator gets us very, very close to that. And if we rounded this to 3 decimals, we'd still have 50.000, but pretty quick way to get that calculation. And then the units of R of t are in liters per hour, and then when we take the derivative, we're going to have to divide by units of the independent variable, and the independent variable is being measured in hours. So we're going to have liters per hour, or liters per hour squared, and what this means within the context of the problem is the rate at which water drains from the tank is increasing, since that's a positive value for the derivative, by 50 liters per hour at t equals 3. And then in part D, not a lot to do here. A little bit different type of question though. It says write but do not solve an equation involving an integral to find the time A when the amount of water in the tank is 9,000 liters. So we know there are initially 12,000 liters, and then we would subtract how much water has drained from the tank. And we want to know when that is equal to 9,000. So we're starting with 12,000 minus how much is drained equals 9,000. Now the one tricky thing is making sure this integral gets composed correctly. Since this R of t represents the rate at which water drains, the integral of it from 0 up to some value is going to represent how much water has drained from 0 up to that value. So if we want to know when there are going to be 9,000 liters left in the tank, start with the 12,000 minus how much water has drained, since we're integrating the rate of change of the draining water across the interval from 0 to a, and then the solution to this, if we were able to find it, would be the a value where the amount of water in the tank is exactly 9,000 liters.